Going back to what we have done before, all the equations that you need. One is for displacement, which is displacement in simple harmonic motion. Then you have the velocity. I'm rewriting it once again. Y equal to r sine omega t. V is equal to r omega cosine omega t. Acceleration is negative r omega squared sine omega t. And then we have the acceleration in terms of displacement. And we have the velocity at any position. So these are the main equations in simple harmonic motion. Okay, main equations. You can just use this equation and do whatever you want. As you can see here, the maximum amplitude, maximum displacement is the amplitude, maximum velocity is the r omega, and maximum acceleration is r omega squared, the magnitude, r omega squared. And the other thing you should be aware of is where in an oscillation is the acceleration maximum. Where is the acceleration maximum? Where is the acceleration maximum in which part of the oscillation? Like as it is moving on, this is a pendulum, right? So this is moving back and forth. Where is the acceleration maximum? In the middle or the extreme ends? Extreme ends. Acceleration is, what is the acceleration maximum equation? Maximum acceleration is r omega square. R is the amplitude. Acceleration is 0 in the middle. Look at the acceleration expression. Where y is 0, acceleration is 0. That means when there is no displacement in this position, the acceleration is 0. So as it is swinging by, the acceleration is 0 in the middle. And at the extreme ends, the acceleration value is maximum. So when it is here, the acceleration is omega square, or which way? That way. And on this side, where is the acceleration? It is this way, r omega square again. Okay? Where is the velocity maximum? In the middle. And velocity is 0 at the ends. Where's the displacement maximum? At the ends, because displacement maximum is amplitude, which is this. So that's basically a simple pendulum. We'll be working with an experiment with this simple pendulum sometime. So what is the definition of simple harmonic motion comes from one of these equations. The definition of simple harmonic motion. What did I say simple harmonic motion is? It's a periodic to and fro motion, right? But our definition is not complete. This is basically the definition of simple harmonic motion. That is the definition of simple harmonic motion. So write down the definition of simple harmonic motion. It's a periodic to and fro motion. It's a periodic to and fro motion such that the acceleration is directly proportional to the displacement. Acceleration is directly proportional to the displacement. And the acceleration is always directed to the mean position. So what is the definition of simple harmonic motion? It's a periodic to and fro motion where the object is moving in such a way that the acceleration is directly proportional to the displacement and it is directed towards the mean position. The acceleration is always directed towards the mean position. Acceleration is directed towards the mean position. That is the definition of simple harmonic. So if you see any motion where the acceleration is directly proportional to the displacement, and it is directed towards the main position, then that is simple harmonic. Okay? So can you consider the simple harmonic motion? Like, I'll show you some motions. This one. Is this simple harmonic? Why is it not simple harmonic? Isn't it kind of periodic to and from motion?
Because it doesn't have the same mean position each time.
And not only that, what is supposed to be the acceleration at the mean position?
Max.
Zero. This is zero? This is 9.8. So what's the acceleration all through? Negative 9.8. And at that spot where it hits the table, there's a very high acceleration only for that moment, and after that again negative 9.8. So this is definitely not simple harmonic. Do you understand? So if you want to consider something as simple harmonic, it has to follow this thing. It has to be proportional to the displacement, wherever it is. It has to be proportional to the displacement. And it should be directed towards the mean position. Then yes, it is simple harmonic. So if something is moving in such a way that it follows these conditions, then it is called simple harmonic. Another example. That's the Earth. If I make a hole here, I make a hole, long hole, all the way to China. Okay. I make a hole from here right through the center, all the way down. And assuming it is evacuated, well, these are all impossible things anyway. So making a hole all the way from here to here, a total distance of 8,000 miles. Going right through the center, that too. These are all imaginable. Okay, so just imagine that you have this condition, you have a tube that is running all the way. Just imagine there's a well that goes all the way down to the other side of the Earth. Okay? Is that going to split the Earth into two? Will it split the Earth into two? Definitely no. How can it split the Earth into two? It's just a hole. It's not a complete cut. It's not a two pieces like that. It's just a hole. It's not going to do anything. All right, so let's imagine that you have this well like this, and you jump into it. What will be the acceleration when you're here? Which way? 9.8? Which way?
Down.
And what is the acceleration here? 0. And as you go down here, what's the acceleration here? 9.8 up.
Well.
Is that simple harmonic?
Yes.
It is. This is simple harmonic motion. So what will happen is you drop from there, it'll be 9.8 here. As you go down, it'll be 4.9 here. It's proportional. We did it in gravity, right? And then when you go to the center, it's 0. And then when you go here, it'll be 4.9, but that way. And over here, it'll be 9.8 that way. And it is following the conditions for simple harmonic motion, which is acceleration is proportional to the displacement. However far you are from the mean position, the acceleration is going to be. So it's 9.8, 4.9, 0, 4.9, 9.8, and it is directed always towards this point. So it is simple harmonic. So that will be simple harmonic. Yeah.
And when you stop, it's exactly the same.
Yeah, you'll stop exactly there and turn around. That is assuming it is completely evacuated. I mean, if there is air resistance, of course there is. I mean, if you're falling off and if there is a drag because there is air resistance, you won't reach there. You won't reach there. So let's think more practically, not theoretically into it. So if you jump like this, how long will it take for you to reach there? So if you can actually drop packages from here to China, how long will it take from here to reach the other end? Okay, so what is considered a period over here? When you drop something, it goes all the way here and comes back. That is one period. All right, that's called one period. And What's the amplitude here?
4,000.
Amplitude. 4,000 miles. 4,000 miles is the amplitude.
Oh, yeah.
The amplitude is this. This is the mean position. That's the amplitude. And you go to the same distance on the other side. That's another amplitude. Come back. So, how long does it take for it to go there alone is my question. So, if you can find the time period, which is the time for it to go and come back, then you can actually figure this out. Is there anything that you can start with to help you? Do you have any information? We have a solid information, which is what?
Acceleration.
We have the acceleration maximum. We have the maximum acceleration and r omega square. R is the amplitude, we know. We know the acceleration, we know the amplitude. Can you find omega? And if you can find omega, can you find the time period?
Yeah.
Go ahead. Work it out. So 9.8 is equal to r. R is the amplitude, which is 4,000 miles. We don't want it miles. We want it in meters. We want it in meters. So 6,400 kilometers. So this is the amplitude in meters. And omega square,
Wait, is it 6,000?
6,400 kilometers. So in meters. So what is omega? Find out. How much is omega? Just leave it on the calculator. How much is omega? Work it out. These are things that you should work it out so that you'll know where you're getting stuck here.
0.0.
Now tell me in scientific notations.
3.9 times.
Give me more digits.
3.913.
Okay.
3?
10 power?
10 to the negative third.
Yeah, that sounds like
1.237 times something like that.
1.237 times 10 to the third.
Are you doing? Okay, you did the square root, right?
Yes.
Check it out and see what happened.
You 6,000,000.
Yeah. Well, I did 6.
There's something there.
One last.
So what is it? 1 point?
1.237 times 10 to the negative third.
Radians per second. But you know omega is 2 pi over capital T. So what is time period? Time period is 2 pi over omega. Find that out. Find that out. What is time period? 2 pi divided by this answer. That's why I said leave the answer as it is. 2 pi divided by the answer.
5,077.58.
How much?
5,077.58.
Seconds. How many minutes is that?
284.
84 minutes. It's on the other side.
That's a long time.
Wrong.
Oh.
What is 84 minutes? It's a time period, which is the time taken for it to go down and come back up. So what is it? What is the time it takes only to go down? So 42 minutes it takes for it to just go to the other side. So if you drop something into an evacuated well that goes all the way down, it should reach down there in 42 minutes.
Wow.
Yeah. Well, this is the kind of system that they were kind of trying to do, postal system, but not like through the center of the earth because it's impossible. But they were trying to do it from one place to like across like this. I think they're still trying to do it. It's a tunnel system.
Is it possible?
It's possible.
How would you have the acceleration that like goes that?
Because over here when you release it, acceleration due to gravity is this way, but it'll have a component in that direction. It'll have a component in that direction. This acceleration is 9.8, but it'll have a component in that direction.
Yeah, but based in the middle, it's gonna just go straight down.
No, I mean it is.
What do you think?
It'll have
Right above it,
velocity.
will it still have?
The building slip and slide.
It is evacuated and it is magnetically levitated also.
Oh, that, okay.
It's levitated. It's like not touching anywhere. So it's a tunnel and it's magnetically levitated. and all it's like a capsule that it just goes through, and it goes all the way down there to the other side. It's an evacuated capsule basically. And when it comes here, the gravity is right straight down. What is the component of that in that direction? 0, which is what actually simple harmonic motion's condition is. There's no acceleration here, and so it goes to the other side, and that will cover a good distance. But problem is making the tunnel. That's a big issue. But if that can be done, you can humans can actually go from one place to other place in very little time. Like for example, from New York to California, you can reach there very fast.
How fast would you go?
I mean, it depends. The speeds can, of course, you don't have to be completely dependent on gravity. You don't have to just let it go only by gravity. You can just power it up initially itself, and so you can actually get some extra benefit, and then slow down there later on. And I think it takes very little time. I mean, by calculations, it takes very little time to reach. I mean, this is a project that's going on. They're planning this kind of thing. I don't know what it's called. It's a project that they're planning, and they're trying to invest money into it, and there are shares being pushed out and all these things. So if it works, that'll be a easy thing to travel from New York to California. Just go into the thing and shoot yourself there, and you'll reach there. And because there's no stop anywhere else, it just goes straight. Yeah,
How would that be done safely? Would you be in some type of like vehicle?
it is a capsule. Yeah. It's a sealed capsule, and
So it's pretty fast.
it should be very fast. So how long does it actually take to fly from New York to California?
Couple days.
Wait, I'm talking about driving.
I'm not asking you flying like that. No. No. 7 hours. No. I'm not talking about Cessna. I'm talking about a real Boeing. How much time? Maybe 3 hours? 4 hours?
Yeah.
3 hours? No. 3 hours is a little too short, but maybe 4 hours. 4 or 5 hours, maybe. 4.5 hours, possibly. Check it out and see. 4.5 hours?
I'm trying to see if people listen to
Maybe 4 hours. I think it's between 4 and 5. Just check. Flying time, the Boeing. It takes 5 hours to go. And instead of that 5 hours, imagine you're able to go there in just 1 hour.
I don't like it. Say it one more time.
If you can just go there in just 1 hour in this capsule or 30 minutes in that capsule, it's wonderful.
Because it'll take out the aviation industry. It'll like hurt them.
I feel like it would cost less.
They did that.
Well, this is only for rich people. It's not for a common person.
Yeah, also.
It's only for people like Trump. Put him inside and shoot him.
We just have unethical flying.
All right. Well, they have to go through all the technical issues. What if you get stuck right in the middle? And all right. So, what is the definition of simple harmonic motion? Something that oscillates back and forth, having a timing. So it should be periodic, and the acceleration should be directed always towards the mean position, and its acceleration must be directly proportional to the displacement. If all these things are satisfied, then it should be simple harmonic. And understand that in simple harmonic motion, like the other thing that we did was the graph with respect to time. How was the displacement graph? That was the displacement graph. How was the acceleration graph? Well, it doesn't have to be the same amplitude. I'm just showing the way it varies. This could have a different amplitude, right? Because this one's amplitude is r omega squared, whereas this one is just r. So for different y-axis scales, that is the acceleration. So this is acceleration, and that is displacement. How is the velocity graph?
Cosine.
Cosine. So that's the velocity graph. That's the velocity graph. And again, look at this graph and you can see more details. Displacement, velocity, acceleration. The slope of this line will give you this line, right?
Yes.
The slope of this will give you acceleration. Now look back here. Look at the black line here. Which way is the slope?
Positive.
Positive, right? It's a positive velocity. You see it? What's the slope of this black line right there? Right there.
Zero.
Zero velocity. What's the slope of this black line here? Negative max. What's the slope of this line here? Zero. Zero velocity. So you see the connection there? Slopes. Now look at this one. Acceleration graph. Slope of the velocity graph. Here is the velocity graph. What's the slope of this blue line? Here. Zero. What's the slope of the blue line here? Negative max. Right? And slope of this blue line here?
Zero.
Acceleration is zero. Slope of this line here? Positive max. Do you get it? So if you're given a graph of something varying against time, and if you're asked to plot the other ones, this is what you need to really follow, and you should be able to get it. I'll show you a sample. Let's say, for example, if I'm giving you this graph. This is the velocity, acceleration. Acceleration versus time graph. I'm giving the acceleration versus time graph. If the acceleration versus time graph is this. If this is the acceleration versus time graph, on the same scale, how is it going to be the velocity graph? How do you plot the velocity graph right here? Where do you start from? How do you plot the velocity graph on this same scale? Where should you start it from?
Other side.
When the acceleration is maximum, what's the velocity? Zero. That means it has to start from here. Correct? The velocity must start from here. But now, starting from there is good. Now, check. Is it going this way? This way. That's our question next. What is the What is this? What is the acceleration value here? At this point, acceleration value is zero. That means the slope of the velocity graph must be
Zero.
well. The slope can be zero here as well as there. Doesn't explain again. So how do you actually get the real graph? Is it going that way or that way? The best thing to do is to go back to this graph. It's easy to draw this graph, right? Once you draw this graph, what you do is this axis, just scoot this axis till you get this acceleration shape like that. Where's the acceleration graph? The red one, right? Move this thing all the way till here. Can you see the acceleration graph looking exactly the same way? Where's the velocity graph here? This one? That's the velocity graph. So you can just draw the velocity graph from there. No confusions there because you're comparing with that graph. You understand what I did? Now look at this graph and see, alright, what's the slope here? Zero, that's zero. What's the slope here? That's negative. Coming. Just move the scale and you'll get the other graphs. How is the displacement going to be if it is here? Like see? If that is the acceleration, displacement is going that way. Opposite. Displacement is easy to do because it's just the opposite of acceleration. If acceleration is this, then the displacement is going to be the other way. Okay? Any questions on this graph? So if you're given only a tiny portion of a graph, you should be able to really picturize where the other graphs are going to be. And the other thing is, from any graph, you should be able to find out the very important clue, which is time period. So if you're given a graph like this, if you're given a graph like that, and they said it is the acceleration graph, only this much is given to you. This is the acceleration graph. And they give you this one is 0 and that one is 0.01, and what's the time period? 0.04, because this is only a quarter of the time period. So look at the graph and you get the clue that, okay, this is just a quarter of a time period, so that means the time period is 0.04. So you got the time period, which means you know how to find the omega, right?
Yeah.
And so you know the omega, and you have the maximum acceleration right there on the scale, so you can get all the other details. You understood? So yeah, the questions can be anything. You just have to really merge into the question and find out, okay, what clue can I get from this particular problem? What equation can I use to get there, to find out the maximum velocity and the maximum acceleration or acceleration at any point or any position or any time. All those things can be done. All right. The next one is a simple pendulum. A simple pendulum. How do you construct a simple pendulum? Remember, this is going to be a lab activity that you will be doing at home. So I will give you further directions about it. Okay? Now, since you have homework to do this weekend, I'm not giving you that assignment, but the assignment is going to come up soon. It will be a lab that you do at home. Very easy to construct a simple pendulum. All you need is a string and something heavy. Right? Now, here, this one is constructed by one of the students. Yeah, this one is a simple pendulum. Of course, you tied the string like this, and so it's a fixed length. But you can construct pendulums of any length. All you need is a string and a bob. Okay? All right, Jay? All you need is that. So what can you use for a pendulum bob? You can use a lock. A padlock will be fine. Or if you have this, you can do this. It's purely up to you. But yeah, that is a simple pendulum. And you're going to study how the simple pendulum, the period of the simple pendulum depends on factors. What are the factors the period depends on? So let's discuss this pendulum in detail. What exactly is happening in the case of a simple pendulum? So that is the pendulum. That's a pendulum. So when the pendulum is brought here and released, that is the amplitude. When you bring the pendulum to one place like that and then release it, that is the amplitude. Wherever you release it, that is the amplitude, right? So that this whole thing is the amplitude, R. Now when you release it from there, what happens to the bob? Will it stay there? What's going to happen? It's going to move. Which way? It's going to move this way. What is making it go this way? Gravity is acting downwards, though. Gravity is acting straight down. So why is it going this way?
The weight and lack of tension.
Lack of tension. Okay, if the string was exactly this way, and then if I released it, the bob is going to start moving right down because gravity is pulling it down straight. Okay? But at this point, it's not moving. It's going to go this way. Why is it going that way and not anywhere else? Is my question. Let's discuss the forces acting on the bob. What are the forces acting on the bob at that spot? Gravity straight downward. What else? Huh? Centripetal force is not a force. Remember that, right? You did say, what is centripetal force? It's a net force, exactly. It is a net force. It's not one force you can identify. Centripetal force, and centripetal force mainly is the net force for an object going in a circular path. But right now it's not even moving. I just released it. I'm discussing what forces are actually acting on it. Yes?
The tension from the string.
The tension from the string pulling it up. Yes, there's a tension pulling it up. That's the other force. Now, if the angle of the swing is theta, I can split mg into two components. mg, someone left it open. Totally dry. The tension has two components. No, not tension, this one. The weight has two components. One is this component, and the other is this component. If this angle is theta, what is this angle here? Is that theta? If this angle is theta here, this is angle theta also. So when I split mg into two components, one is this way and one is this way, what component of mg is acting this way? Here. What component of mg is this way? mg cosine theta. And that explains to you what component this one is. What is this one? mg sine theta. So what is happening over here is, when I split mg into two components, we have mg sine theta pulling it this way and mg cosine theta pulling it that way. Now what do you know about the tension and mg cosine theta? They are equal to each other. Why? Because this bob is neither going this way or that way. Which means the tension and mg cosine theta cancel off, leaving behind only one force, which is mg sine theta. That is the net force. That is acting which way? This way. And that is why the bob is beginning to go that way. Do you get it? So why is the bob kind of swinging to this position? What is bringing it down is mg sine theta. Yeah.
Why can't we just split it up into two components like that?
We did it.
Yeah, but like why?
Because then we can actually find out the resultant. There are two forces acting, tension and mg. What's the resultant of all this? Is just mg sine theta. So the net force acting on it is just mg sine theta. So the net force is mg sine theta. Which way? Mean position. And so I will call this a restoring force. So the restoring force is that. And because it's a restoring force, I'm going to just say F is equal to negative mg sine theta. Because this F is just a force. And restoring force, why is it negative? Because it's a restoring force. It's kind of backward. That means when I swing it one way, it's trying to bring it back. If I swing it this way, it's going to be pulling it this way, right? So that's the restoring force. If that's the restoring force, what is the acceleration? If that's the restoring force, what is the acceleration?
G sine.
Negative?
G sine.
There we go. That is the acceleration. Do you understand so far? This is the acceleration. And it's g sine theta. Now here we use a small angle approximation. And what's a small angle approximation? This is a very important thing in math. Small angle approximation is this. if theta is very small, sine of the angle is approximately equal to tan of the angle and is approximately equal to the angle itself in radians. That is called the small angle approximation. And it's something that we will use even next year. So when I remind you of, have you done small angle approximation, you should know what it is. And this is something that is used in trigonometry sometimes to cancel off sine theta and tan theta. If you know that the angle is very small, you can use this. Take your calculator and just type in sine 5 degrees, sine 5. You saw the answer? Now tan 5. Put tan 5 and see what you get. Is it very similar? No?
Yeah,
You have to put it in degree mode. Put it in degree mode. Sine 5 degrees and tan 5 degrees, they're same? Okay, can you convert 5 degrees to radians and find out how much it is? Convert 5 degrees to radians means times it by pi divided by 180. Do you get the same answer almost?
Yeah.
That's exactly what we mean by small angle approach. So when the angle is small, so 5 degrees is small enough to be considered a small angle. Do you understand? What about 10 degrees? Sine 10 compared with tan 10. That's also pretty close. But you can see that it's not as close as the other one. Right? So when the angle is small, like 1 degree or 2 degrees and all that, sine theta and tan theta, they're all basically the same. That is called small angle approximation. Now, if you go to 30 degrees, well, that is not small anymore. What is sine 30? Is 0.5. What is tan 30? 0.57. See, it's kind of going off. So, yes, as the angle becomes bigger and bigger, this approximation is going out. So, what can be considered a small angle? 5 degrees is good enough to be considered a small angle. 10 degrees, consider, you can still take it. But again, understand that you're stretching the limits there. Using the small angle approximation, sine theta can be considered just theta. So therefore, this equation becomes A is equal to negative G theta, where theta is measured in radians. Theta is measured in radians. So at any position, like let's call this as a displacement y. At any displacement, this need not be at the very end. It need not be at the very end. It can be at any point. So that means as the pendulum bob is moving at any spot, this is what's happening. The acceleration at any spot at this distance y is this. Now what's the connection between y and this length L? What's the connection between y and L and theta?
Wait, is y the whole like?
Y is this arc length.
Is L the?
L is the length of the pendulum.
L theta equals y.
L theta is equal to y, so you know that theta is equal to L over y, right? Y over L, sorry. Theta is equal to the arc length over the radius. Arc length over the radius. Do you understand this? We've done this in detail in circular motion. So bring that here. Acceleration is equal to negative G L y over L. And I can rewrite that as acceleration is equal to negative G over L and y. G over L. Now, is G a constant? Is L a constant? So G over L is a constant by itself. And now what do you see in this equation? since you can see in this equation, acceleration is directly proportional to displacement. You see it? And is directed towards the mean position. Do you see that equation clearly displaying those two qualities? This equation displays the two qualities that are needed to conclude that this motion is simple harmonic. Acceleration is directly proportional to displacement, and acceleration is directed towards the mean position. Those are the two things that are required to conclude that this movement is simple harmonic in nature. And if it is simple harmonic, what do you have? What do you make this? What is this equation comparable to? This is the acceleration. Minus omega square. Y. What's that? Yeah.
Well, if it's a big angle, does that still work?
Now, that is why when you're doing this, one of the precautions is this. When you're doing the pendulum experiment, you cannot do this. Because we are going to derive the equation by assuming the small angle approximation. So your oscillation should not be wild oscillations. Instead, the oscillation should not be more than 5 degrees or 10 degrees. So if you just move it like this, that's it. When you do this, you are able to get close to what we are trying to derive. Yes.
So does that mean like G over L is equal to W over omega squared?
W. Oh.
I changed it.
Okay. So yes, you're right. Omega square is G over L. And that's what we are picking up on. So omega square is equal to G over L. And what is omega? 2 pi over? So 2 pi over capital T, the whole square, is equal to G over L. Which means time period over 2 pi, the whole square, is equal to L over G. I just flipped it. Which means, what is this? Square root of L over. So what is time period? 2 pi times square root of. That is the equation of the simple pendulum. So I've derived that equation by the simple harmonic motion concept. That is an equation. Time period is equal to 2 pi square root of L over G. So what do you understand from that equation? What do you understand from that equation? The time period depends on what factors? Length and gravity. That means if I shorten the length, what should happen to the time period? If I shorten the length, it takes shorter time to complete an oscillation. Do you see it? The longer pendulums will take more time to complete the oscillation. The other factor is G, gravity. So if I do the same thing, instead of doing it on the earth, if I take it to the moon and do it, it should be much longer. Time period will be more because G is smaller there, right? So the oscillation of the pendulum is going to be slower on the moon. What if I take it to a satellite where it is in weightlessness? So acceleration due to gravity, apparent acceleration due to gravity is 0. So what will happen when I release it? It will stay there. Which is, so what is the G value? What is the apparent G on in weightlessness? 0. Something divided by 0 is? Something divided by 0 is? Something divided by 0 is? Infinite. Something divided by 0 is infinite. That's not it though. Something divided by 0 is infinite, which means time period is? That means it takes forever to go and oscillate once.
Forever.
You understand that? Anything divided by 0, don't just say it's error. No, anything divided by 0 is infinite. Okay, so the time period depends on factors. Okay, now what will happen if I change the pendulum's mass? Nothing. Pendulum's mass has nothing to do with the time period. You get it? Now that being said, imagine you went to a park and you saw a swing. You saw a swing and you sat on the swing. You sat on the swing and you are swinging. So there's a time period, right? After some time you get bored and you just stand on the swing and swing. Will the time period be the same or different? Why?
Because your center of gravity is
It's
you shorten your distance from your center of gravity.
exactly. So what happens when you stand? You're standing up, which means the center of gravity is not here, it's somewhere here, which means you're shortening the effective length. So what is L? L is the distance from the point of suspension to the center of gravity, not to the end of the object. That is why the center of gravity is an important thing. So when you do the lab at home, the center of gravity is something that you're supposed to look into. Approximately where is the center of gravity? So your measurements should be from there until the point of suspension. You get it? So that is what a pendulum is now. So the factors are very simple. Length, gravity, most importantly length. Now if you try to look at your leg, when you walk, our leg is a pendulum. Our leg is a pendulum, look at that. It is suspended here and it has its own center of gravity. So when you're walking in a very casual manner, the timing is not decided by you, it is decided by the length of the leg. And that's one of the reasons why a tall person appears to be walking in a lazy fashion. And a short person appears to be very brisk. A short person, have you seen the short person walk?
Yes.
How does a short person walk like this? And what's happening over there is, it doesn't take much time for the leg to swing to the next location. So the timing is less. And so the short person will walk very brisk. Whereas a lazy person, think of a tall player, like they take time to swing the leg. Why? Because the length of the pendulum is bigger. Now some people have legs shaped like this. So where is the center of gravity of this pendulum? Much higher. Which means they'll take very little time to swing their legs. Think now when you see a person walking, just look at the structure and you'll say clearly. What changes the timing of their walk is the structure of their legs. Now similar to this we have a pendulum which is the spring pendulum. Okay? Now in a spring pendulum the equation is exactly similar, but this will be the mass that is suspended at the end of the pendulum, and this is the force constant. So you can read through that part of it and then do the homework assignment.
Me, Tom, and Sam are beard.